what this is all about really is the Permian granites in Devonian basins. Now, if you take one thing away from this, take that away, that the basins, all these basins are of Devonian age, and the granites are all Permian. And there's a big old time difference in between. The whole of the Carboniferous is in between those, okay? So it's not, the granites were intruded into the sediments when they were sediments. They'd already had a very, very long time before the granites came along. Now, this is a diagram that I've used before because we look at the pattern of these basins as we've worked our way down here through all the other field trips. And there's a whole series, the Colne Basin, Tavy, South Devon, Loo, and down here we're in a thing called the Gramscatho Basin, which I think is a terrific name. Paleogeography for the Devonian. So this is when the sediments were laid down, okay? Britain is here. Southwest England's on that margin here. There's just two different versions of it. But essentially, this is Laurussia on the northern side. And then there's the Rheic Ocean, which is a deep ocean. And on the other side was Gondwana. And Gondwana was gradually moving towards Laurussia through this time. But in the Devonian, there was probably subduction going on along here and probably in the other direction as well. But the Southwest England, which is there, was basically within an extensional back arc basin behind this subduction front here. So in the Devonian, this was extensional before it all collided. So this is the rift basins, extensional rifts moving on, and we've talked about this before. So Torquay High, the blue is the limestones, Brixham High, and then you go off into the Loo Basin, and then the next one on, somewhere over here, is the Gramscatho Basin. But basically we're getting deeper. So shallow up here, getting slightly deeper, Loo Basin, deeper water, and then the Gramscatho Basin is actually a deep water basin, deep water sediments. So what do the Gramscatho Basin, Gramscatho sediments look like? Well, essentially there are two types, fundamentally. There are the Gramscatho beds themselves, which are sandstones. And these, we will see the outcrop on the north coast of the far end of Cornwall. And as you can see, lots of nice laterally continuous sandstones. The other fascies are slates, or when they were laid down, mudstones. They are fantastically folded and distorted and all sorts of things. I'll show you some more pictures of those as well. So those are the two fundamental fascies types within that Gramscatho Basin. So the sandstones are like this. So nicely laterally continuous sandstones with sharp bases, graded, rippled tops, and interbedded mudstones. These are classic turbidites, if you're familiar with that. So this is the turbidite sequence, core space, erosive core space, massive sands, then rippled sands and plain bedded sands, and then a graded top. And that's exactly what you're seeing here. And they are deposited from these things called turbidity currents. Now, if you're not familiar with these, they basically form on slopes, so on the basin margin. And what happens is you have something to kick it off, and I'll talk about that in a minute. And then a flow, a gravity flow, will start moving down the slope. And as it does that, basically the head, the front of the turbidity current here, the head, is very turbulent. And what it will do is it will erode what's underneath, and that will become entrained within the flow itself. So as the flow moves, it picks up more and more sediment, fine-grained sediment, and becomes, its density goes up, and so it will just keep on going. And they can go for a very long distance. But as it goes through, you basically got the coarse material at the base, and by the time you get to the tail, you're just getting the finer grain material at the end. And so that sequence that you see, the ordinary sequence down here, is basically the passage of a turbidity current through wherever it is you're standing. But there are various forms of these sorts of flows. They don't have to all be just ordinary turbidity currents. There are all sorts of things, all the way from debris flows, where basically the slope fails and then everything just slumps down the slope, through all the way down to the high density turbidites, which I've been talking about, and these things called low density turbidites, which I'll also show you. And all sorts of things in between. Now, what might kick these off, there's a variety of things that can kick these off, one of which is just, typically they will form off the front of a delta or something like that, where you've got sediment being supplied down a river, and if you've got a sudden, a storm or something onshore, you've got a lot of material coming down the river, it goes into suspension at the front of the river, and once it gets to the slope, bang, it goes off down that slope and starts producing these sorts of things. But that's, you can also get the same thing if you've got a big storm actually on a on a continental margin, then you can stir up an awful lot of sediment actually into the column, and that can go off the edge, and that can produce its own flows, or indeed just, well, like I say, you can have slope failure, which will produce debris flows, but can also basically by entrainment and turbulence can produce turbidites. So those are the, and usually you get these lovely thick sandstones like this, decimeter up to meters thick, but usually sort of decimeters. But these are the Mylor slates, and they are related. And so they are absolutely beautiful, and they get distorted and folded and fractured and all the rest of it. And you get these fabulous sets of folds. And these are low density turbidites, or possibly hemipelagites. Now, hemipelagite is basically where you've got big disturbance in the sediment, and that cloud of sediment moves out from the margin and then just basically settles out. So you can get things just from literally raining down after a big old storm, as well as these flows. But these are just beautiful. And this is the model, if you like, for low density turbidites, where you've got bands of things that note the scale here, that's a centimeter. So multiple silt and sand laminae through here, and then back into basically mudstone. So the interesting thing here is that, each one of these could be its own flow, or it could be part of a multiple flow. Really difficult to see where the base of any particular flow is, but they're all sharp-based, and they are clearly rippled. So, and this is within, this sort of thing is not just folding. This is rippling within it, and you get cross-bedding, cross-lamination rather, cross-bedding. So low-density turbidites. and so beautiful exposures of them. But also within the Mylor slates, you get this. So this is a completely different facies. This is basically a debris flow. So this is where the slope itself has failed, probably a slope of Mylor mudstones and sandstones, and it's just all haphazard. There's a bit of bedding in there, but essentially it's haphazard throughout the whole thing with all sorts of different grain sizes in here. But they are beautiful. And they do get folded, and you get these quartz veins coming through them. And they have also been, you must remember, they've been compacted. So when they were originally flowed, they must have been much, much thicker. They've been compacted, and you can see in places where quite late stage quartz veins, little quartz veins have gone through them, and they've been compacted, so they're going like this, interolithic quartz veins. Right, so Devonian sediments, the sandstones, the big thick sandstones, and then the slates and the thin silts and the rest. But there's one other Devonian marine facies, and that's basalts. So around St. Ives, you get these wonderful pillow basalts. And if I just show you this, you can clearly see the pillow structure within these. It's just ordinary basalt, but the pillows form. I'm sure you've all seen the pictures of lava being erupted underwater, and of course the water chills it, and then it breaks through and forms another pillow and breaks, and so you get this particular facies. So that's pillow basalts, Devonian pillow basalts. So this is our geological map, and I will refer back to this on a number of occasions, okay? So what we're looking at here is the big lump of red here is the Land's End granite. And then all of this, I suppose it looks green here, is the Mylor slate. Up here, this slightly darker color is the Gramscatho sandstones. And then that light colored red, pink, I suppose, and in fact these dark bits here are the basalts, the pillow basalts. But you can also see lots of other things on here, lots of big faults running across northwest, southeast. Yes, and also lots of these are sort of orange colored things going in this direction and various other things going in this direction. And over here, you see lots of dotted lines going off in this way. And over here, they're going that way. And these are the mineral lodes. Oh, and the orange bits are, well, we'll come to those later. So, sort of panning out a bit, seeing where that is. You've got the Land's End granite there, but you've got a whole series of granites. We all know there's Carmenellis, St Austell, Bodmin, and Dartmoor. But there's also the Ars of Scilly, and there are also granites exposed at the seabed out here at a place called Hague Fras. And if you see, that's the 200 meter depth contour. I guess that's going to be the 150, and that's the 100. So during the last ice age, all of this was exposed, and those would have been exposed as well. So quite a lot of different bits of granite at the surface. And there are all sorts of other little bits of granite around, one of which is here, which is the tregonning godolphin granite, which I'll talk about. And there's lots of other little bits and pieces around. Now, this is the important diagram here. This is the gravity data for that same area. And the gravity data, because granite is actually quite low density, it shows up quite well on gravity data. And what you see here is a continuous gravity low right the way through. So that's the outline of the of southwest England there, and it goes right the way through. And then there's a jump, and this is Hague Frass over here. So it would seem that these are connected, that they are one large batholith like this. This is a model of it going all the way down and all the way offshore. But the gravity modelling shows that they don't just go down forever. They are slabs. It's a slab of rock within the crust. And they generally, this is the south and that's the north on these diagrams. So doing cross sections through gravity modelling on cross sections seems to show that the southern margins are very steep, the northern margins are much more shallow, and that probably the feeders, if you like, feeder pipes for this were on the southern margin, and it came up there and then spread out. But there, it seems to be tabular, about 3 to 5 kilometers thick. But they're not all the same granites. There are some very important differences between the various granites, both textural and mineralogical. So the Land's End granite down here is a biotite granite, as is Dartmoor up here. But both Bodmin and Carmenellis are completely different. They're two mica granites. They've got biotite and muscovite in them. And there are some granites here, like the tregonning granite around here, which has topaz and lithium mica in it. Completely different. So that's interesting. The other thing that these colours represent is the grain size. So this is the textural difference. So there are fine grain granites. So for example, that grey bit there, we'll come back to that. That is fine grain granite. Whereas most of it is really coarse grain granite and has megacrysts in it, big feldspar crystals within it. Yes. And they're not even the same age. So, so this is the entirety of the Permian, basically. And unfortunately, this diagram has time going that way, downwards. The earliest ones were Carmenellis, Bodmin. These are small things. Then Dartmoor comes along. Actually, Land's End is relatively late in terms of its emplacement compared to some of the others. But it's over 30 million years that these were in place, and it didn't all happen at once, and it didn't all happen in the same way or with the same source material. So if we just go back to this, the BGS sheet, and we look up here in this top corner, because this is a really interesting map. This is a distribution of potassium feldspar megacrysts in the Land's End granite. So you have the pink color is coarse-grained granite, and the darker color is fine-grained granite. But then the dots are the amount of megacrysts, and I'll show you what these are in a minute. So lots and lots of dots is abundantly megacrystic, and then you've got moderately and areas where there are no megacrysts at all. And even the fine-grained granite. So you get fine-grained granite, some of which has no megacrysts in it, and some of which, well, they do. They have some. So there's quite a lot of variability. Now, we're going to start off just by looking at this point up here, which is Rosewall Hill, which is above St Ives. So that's St Ives down there. And in the distance, that hill over there, that's the Carmenellis granite in the distance. And the reason we've come up to Rosewall Hill, what you're doing is we're on the basic part of the Land's End granite. It's coarse granite with lots of megacrysts. And there they are. Coarse granite, lots of megacrysts. And they're all aligned. So nice, presumably flow indicators. And if you look at it on the other side, then this is what you see. Lots of these, they're platy feldspar crystals, K-feldspar. Just really rather lovely. And the background material is very coarse as well. So that's the standard sort of Land's End granite. But if we go there, so in the middle of this, which is the fine-grained granite, then what you see is this. Go on, spot the phenocryst. I know it's a long way away, but it's very, very light color, okay? I should just point out that's St. Michael's Mount in the background. So St. Michael's Mount, the southern side of St. Michael's Mount is more granite, but it's a different granite. It's not the Land's End granite. And it would seem that it's a granite that extends out to the south rather than being connected to any of this. Anyway, back here, what that granite looks like is this. So light colored, but fine grained. This is from that quarry. And then there's Carmenellis, which over here, so we were up here. That's the island, St. Michael's Mount, thank you. This is, we'll come back to tregonning godolphin, but this is Carmenellis here, with fine grained in the middle and coarse grained around the outside. And if we go there, so Carmenellis is a you can just see it, we're going to go here, is a 2 mica granite, so it's got biotite and muscovite. So this is what it looks like. That's the light brown bits of the muscovite, the dark bits of the biotite, and then quartz and feldspar. And this is from a quarry called Lower Trollvis Quarry. It's worth pointing out that this is a BGS core from this quarry here, and I'll come back to that. There's a reason for that. So anyway, quarries. Why are there quarries? And in fact, there are quite a lot of quarries on the Carmenellis granite. All of these are quarries around the both in the granite itself and also in things called elvens, which we'll talk about in a bit. So why are there so many quarries on Carmenellis? Well, because they built London with it. And you've almost certainly seen it. This is the embankment. Those are the Thames Stairs Arch, which is made of Carmenellis granite, as is Waterloo Station. So you've all walked past it and never really looked, I know. But next time you do, see if you can spot 2 types of mica. Of course, everybody else around you will look at you weirdly, but nevertheless. So let's come back to why that core was taken through a granite. Why would BGS bother to core granite? Well, because on a number of occasions, it's been looked at quite seriously as a potential energy source. This is a map of heat production and heat flow within well, in the whole of southwest England, actually. So there's Carmenellis granite, this is the Land's End granite, and there's quite a lot of heat being produced around here. And that's radiogenic heat. It's actually heat from minerals and, radioactive elements within the granite itself. It's not exploited, but they've looked at it a number of times now. So, okay, that's it. But how does a granite actually get there? Okay, how does it physically get into all that sediment? And it's quite complicated. First of all, let's just sort of down here. So this is, there's a surface. This is the upper crust. This is the lower crust. And this is the mantle down here. So this is partially molten. We're very deep. Low density granitic magma will come up and basically collect together in areas which will then, because this is ductile, the lower crust is ductile, it will begin to form a diapir and rise through that part of the crust. But the upper crust isn't like that at all. And so what happens is that it starts getting in here and you get these fractures. The physical pressure of this thing rises, fractures the overlying crust. Now, this is called stoping, because what happens is that this breaks up and then falls into here, melts, and then creates part of the melt itself. It's not that easy, never is, because of course these things are not, you know, just continuous blobs all the way down. So what actually happens is you have some form of feeder up to a granite magma. This is your stoping and things falling in and then melting into the magma. But basically the surrounding, it is forcing its way up and down. These are then being forced down into the lower crust down here and probably melting at the base and then going back up here and getting recycled. So you've got a very complex system of movement on top of the batholith. Things are breaking up and being broken and fractured and falling in. Underneath it, it's basically pushing down at the same time. Now, I can't show you, you very, very rarely see anything underneath one of these exposed, but the top sometimes is. And here is a bit of it. So this is a cupola, which is a little bit of magma coming up at the top in a place called Porthmeor. And this is the light-coloured stuff is the granite, and you can see the veins, they're filled with granite all over here, more granite over there, and the rest of this is the country rock. Now I'm going to use a number of terms for this. The country rock is basically the Gramscatho formation. So you've got the sands and the mylar slates. But generally, when you're just talking about it as country rock, it's called Killas, Killas, and that's the metamorphosed slates around these things. So here's another example. So this is these are mylar slates. This is granite. All of this is granite. This is actually the tregonning granite. And these big, thick, light-coloured, they are granite sills which connect in to this granite and go off. There are sills of aplite and pegmatite, but essentially they're granitic material injecting out into the surroundings and then either being quenched to produce fine-grained aplite sheets or forming big, coarse pegmatites. Another thing happens towards the end of emplacement is that you get these things. So this is sands, and this brownish bed running all the way along here is actually this. It's a big, thick dike of, it's a late stage quartz porphyry. It's quite a fine-grained rhyolitic matrix, but then with these big feldspar phenocrysts, and there's also a lot of big bits of quartz in there as well. And they're very distinctive, and they weather to this brown color. And you find them They all follow a very, very similar trend, and pretty much anywhere you see, they're all over the Killas, all over the Gramscatho beds. The other thing you see, so this is Senon Cove. Yes, that is a megacrystic granite, and it's got an awful lot of them. But if you look closely at the boulders, what you see, like up here, is this. So that's basically a lump of the killer. It's a lump of the surrounding country rock that's fallen off and gone into the magma chamber itself. And interestingly, within it, there are feldspars forming within this. It's already recrystallizing. And you get all sorts of levels of this going on. So I'm sure you can believe that that's another xenolith. There's some crystals forming on one side of it. There's one down here, but there's also one here. And it's barely a shadow of how it used to be. It's almost completely absorbed into the magma. At Rinsey Head, there's a very interesting exposure in that what you have is what's called a pendant of the mylar slates coming down into the tregonning granite. So on this is all granite. It's granite all along that headland there, and this is slates running up here. And the reason the cove is there at all is because the slates have been eroded out. So that's the sort of the physical edge of the granite. And where we were just then, we were looking at the tregonning granite, and that little bit there, that's the pendant that you see down there. But also, when you go down here, this is the tregonning godolphin granite. So we'll get to see this. And this is one of these other weird granites. It's not quite the same. Well, the tregonning granite literally surrounds the godolphin granite. So there's a godolphin granite, and then the tregonning granite goes around the outside. And it's the tregonning granite that has lithium mica in it, which is very difficult to explain, and topaz. So this is what the granite looks like. And it was funny, I just took this picture as a picture of, feldspar, phenocryst, or quartz, or whatever it was. And the more I look at it, the less I think it's feldspar or quartz, because of the some of the shapes that you're seeing in here. And so just hold that thought. I can't say this one way or another, but what actually is topaz? So topaz is a colorless white, vitreous mineral, hardness of 8, really quite hard, so it would stand out. But the key thing about topaz is it's got fluorine in it. And fluorine is one of these incompatible elements. And incompatible elements are really important in Cornwall. So there's a whole variety of these things. They're basically the things that don't get incorporated in quartz, feldspar, and micas. The stuff that's left over, and they get concentrated as the magma cools, and the quartz and the feldspar and the biotite and muscovite crystallize out. Then everything else gets more and more concentrated, including all these incompatible elements. And there's a whole bunch of them. So fluorine goes into topaz, boron, which I know we've talked about when we went to Dartmoor. It gets incorporated into tourmaline, and there's a lot of tourmaline around. We will see a lot of that. And that's pretty much the only place that boron ends up. Tin is an incompatible element. It goes into cassiterite, which is basically tin oxide, and copper is the same. It goes into chalcopyrite, which is copper iron sulfide. So this is just a straight pick from an earlier thing about the boron problem. So this is tourmaline, okay, and this is it in thin section, and it's worth. I'll read through this. You don't need to read this, but it's worth listening to what it says. So boron is incorporated into tourmaline, usually in an iron-rich form, black form, which is called schorl. So you may have come across that. This forms as a late-stage addition in the primary granite matrix, actually within the granite, but also in pegmatites and veins when the fluids are being ejected out from it. Boron then carries on being mobilized during hydrothermal circulation and replaces feldspars and other minerals in what is called grisons and other zones of hydrothermal alteration. So when you've got very, very hot water, and I do mean very, very, very hot, you know, like hundreds of degrees, then it can do all sorts of damage, but it can also carry the boron with it. So at this time, it can be formed in both the outer zones of the batholith itself, but also in the surrounding sediments, or the metamorphosed country rock, along with all those other ore minerals. Now, what they've done with these sorts of things is they've looked at the petrographic and chemical analysis of tourmalines from the Cornubian batholith and worked out that there is an evolution of tourmaline, of types of tourmaline. And they change their chemistry through time. And that can be related to the amount of tin associated with them. So what you get is high temperature ones and then slightly lower temperature ones. And you can relate the amount of different types of tourmaline to the amount of cassiterite. So this is what it looks like in the field. So veins of it cutting through, and you can see there's intense alteration around some of these veins. This is your hydrothermal alteration. This is grisoning around one of these veins. So it's a fracture that high temperature water has gone through carrying these things, and you've had tourmaline precipitate out, but it's also seriously affected the rock around it. But you also get it in these sort of spots and blebs forming within the granite itself. This is one of those veins. The one side's broken off, so you can see it's, you know, it's right the way through. It's coating the whole thing. And there are other secondary mineralizations associated with it, and that green color is a dead giveaway for copper. So, yeah. Right, and there are all sorts of these which form ore minerals, these incompatible elements that form ore minerals. So copper and tin, but also zinc, arsenic, lead, silver, nickel, uranium, wolfram, manganese, iron. There's gold in there somewhere, manganese. I think that covers most of it. But all of these various elements have been mined at one stage or another, usually during the 1800s in this area of Britain. Now, the ore fields themselves are distributed. Well, this is the distribution of the ore fields. Let's put it that way around. So they're not necessarily all mixed together. So you can get mines that just find tin, and right next door, you can get a mine that has tin and copper in it. And then next door to that, you can have something without any tin at all. And they can be actually along the same lode. So as you go out along lodes, you can get different mineralization along what is almost certainly the same lode. And there's a, yeah, I'll show you on this. So there's a sort of a time, this is temperature. So 700 degrees up here, granite, is a magma at that temperature. Down here it's 100 degrees, so finally you get water instead of whatever else it is up here. But what you get up at these sorts of temperatures is aqueous fluids, magmatic aqueous fluids. You get tourmalinization. You get then breccias, you get cassiterite forming at these sorts of temperatures. And then as you come down, you get different things. So you get copper down here, and arsenic and zinc, and lead and zinc, and silver at relatively low temperatures. So different minerals forming at different temperatures. And so that sequence, when you go from tin to tin and copper, to copper and arsenic, to lead zinc, is essentially one of a temperature gradient. This is an interesting map. It's a BGS thing and it's in stream sediment. So what they've done is they've gone and sampled the streams, the water, well, the sediment in the streams all over the West Country. And this is the concentration of tin in those streams. And as you can see, there's still quite a lot of it down there. But the interesting thing is this almost certainly comes from mine debris and the mine heaps and those sorts of things, rather than being primary. Although quite a lot of streams in the West Country were they were looking for placer deposits within them, so there was quite a lot of stream tin mining as well. But this like I say, is probably from old spoil heaps from mines, and it comes with its own problems in that that's the same map for arsenic. So yeah, do you really want to live here? But there are mines everywhere. You can't move for mines in the West Country. It's actually very difficult to find a map of all the mines. Because this is from a website, and you can't zoom in on it or anything else. It's really annoying. But it's from a website that you can use if you're thinking of building something, and you want to know whether or not your building, whatever it is, will collapse into an old mine. And, you know, clearly, if you're thinking of building something in this area, you need to know this stuff. There are a huge number of mines. So here are some. This is Wheal Prosper. This is on the south coast in Rinsey. And this was, so I showed you Rinsey. Rinsey is the one with the pendant, the actual slates within the granite. So the Rinsey Cove is down there. And this mine was actually mined within the pendant and then extended out into the surrounding areas. So this is where we are. This is Wheal Prosper. There's the pendant sticking in there. And it then got copper and tin in there, went into the granites. And then down here at Trewavus, I'm sure it's pronounced something completely different. That's those sills in the distance, but this was copper mining on the end of in the granites at the end of the same lode. So that's south coast, north coast. So this is I think it's Wheal Edward and Wheal Oates, might be the other way around. Engine houses on the north coast, and you see these engine houses all over the place. And in this end, in this area, you had copper, tin, and arsenic mining on the edge of the Land's End granite. So that's here. And you will have heard of some of these things. Batalic mine is here, and these are the crowns. And then Giva is there, and Levant is here. We'll look at those. But basically, Giva was tin mines, Levant was all of those things, and Batalic had tin, copper, and arsenic. And they were famous, apart from anything else, because they went off under the water. So this is Batalic down here, following a lode that went all the way out, considerable depth over here, down to 450 meters. But Levant from here went down 640 meters under the sea, out here. Giva up here was entirely within, so this is Giva mine, and this is Levant. Levant was basically out under the water, and Giva was in the granite. Sorry, this was in the country rock, in the Killis, whereas this was in the granite. This is possibly the most famous of them all, the most scenic. These are the crowns at Batalic, where they produce copper and tin, with these two scenically placed engine houses. And this is what they look like in the day. Not quite as scenic, but quite extraordinary. And these are some rather wonderful etchings. So the important thing about Batalic is that it had this incline that went all the way underground. And the people would go up, and the stuff and the material would be brought up in these, what were called skips. And they were run by the upper one of these two. So this engine house ran the incline. This one was a vertical shaft. And this is the Prince and Princess of Wales descending the Batalic tin mine, Cornwall, and everybody waving and being happy about it. And this is what it looked like. So here we are up at the surface. That's that top one. That's the vertical shaft coming down there, and they basically went down. What was it? 450 meters below sea level. But famously, in 1863, the chain broke. The slide was about here at the time, the skip rather, and it went all the way down to the bottom. The chain had broken somewhere up here, so it went down to the bottom, followed by several tons of chain. Everybody was indeed killed. 9 people. But the dark patches, which you only just see in this diagram, is basically where the ore was won from within the plane of this thing. But there were lots of these parallel galleries. The other thing that you can still see at Batalic is this. I don't know whether you've ever seen one of these. This is an arsenic labyrinth. So arsenic is, when you mine arsenic, it's in arsenopyrite, so it's a sulfide. And it's about 40% arsenic. It depends on the quality of the ore. But that's not really very saleable. So what you do is you burn the arsenic in a big fire, and then you pass the fumes from that through a series of tunnels this goes backwards and forwards and backwards and forwards and backwards and forwards and backwards and forwards, and then finally up the chimney. The idea being that the arsenic will condense on the side of these tunnels as arsenic oxide, which is 85 to 90% arsenic, which is much more saleable. All you need is some kids to go in here and scrape it off the walls. Presumably small, pale-coloured children who didn't last long. But that's what they did. So Giva was the last working tin mine. It closed in 1990. So, you know, glorious history of tin mining for centuries, went all the way up to 1990. It produced 50,000 tons of what's called black tin, which is basically cassiterite. And it's now a mining museum, and we will go through to this museum on in a couple of weeks, end of next week. But this big shed here, okay, is extraordinary, because when you get cassiterite, what does cassiterite look like? That's what cassiterite looks like. So this is the stuff you physically bring up to the surface. But clearly it's got a lot of other junk in with it. Rock, granite, you know, stuff you don't want. So what you do is you crush this, and then you put it on shaker tables, because cassiterite is quite dense. And you run, it's like a tabletop like this on a slight slope, and you run water on it, and it's got rods across it all the way down, and it shakes. It literally just shakes. And what happens is that it separates out the really dense stuff from the slightly less dense stuff, so you concentrate the cassiterite. And then you can sell that. That's the black tin that they actually sold. And this shed is just for that shed is worth the price of admission in this museum on its own. It's a vast area covered in these tables. And when it was operational, it must have just been amazing, because everything must have been just doing this all the time. And water going down and separating out. Brilliant, just brilliant. The other thing we can do here at Giva is we get to go underground. So this is Wheel, Mexico, and it's a real. It was an adit that was used for tin mining, and the amazing thing about it is that this is the granite. You can see from the way it looks, and this is the killers. It's the country rock. You can actually literally walk along what had been the mineralized edge of the granite batholith. It's rather wonderful. And that's the end. Literally. Thank you.
Do I have to switch that?
No, that's all right. I'll just take it.
Can I ask a question?